My name is Professor Prof Orata. We are continuing with our lectures in thermodynamics, and today we'll calculate the efficiency of a binary system. We saw that last time when we were working with the binary system. We had said that in our binary system, in that circle there, we had two fluids. We had water and mercury. So in that particular vapor circle, unlike the water and Rankine, which you had used earlier on, now we have mercury and we have water. And there were clearly two differences between these two fluids. That we had mercury, which has a relatively high boiling point at about 12.7 bars. The boiling point is about 539 plus degrees centigrade. And it has very low latent heat. It has got very low energy value compared to water. Where we had water, it boils at about 100 degrees centigrade, but has very high latent heat values. Unlike mercury, where the latent heat values are low, relatively low. This one's for water above 2000 kilojoules per kilogram. Now, what is significant about this binary system? Suppose we draw on the temperature entropy profile. The cycle, so let's draw one for the vapor side, for the mercury. Let's have one for the mercury. And then let's have one for the Rankine circle. Water-based, and for the Rankine circle. So we have this for the mercury, Ig system, and we have this for the water system. Now, let's just label the processes 1, 2, 3, 4, 5, call that 6, 7, 8, 9, 10, 11. Let's mark our processes. Mark our processes. So we have the Rankine circle here, and we have the mercury cycle up here. Now, we have said that the mercury has a higher boiling point compared to that of water. So, when you condense the mercury vapor, so we know that the output, remember, it's our turbine, the output, so just the W net in terms of these two systems, the W net here will be H3 minus H6 minus H7, based on our markings of the state points, marking our state points 2 to 3, 6 to 7 for the system. So the network is that. Just remember from first law of thermodynamics for steady state flow processes, that is flow processes, we say that dH plus dC squared over 2 plus GdZ is equals to dW dQ minus dW. W, when you're dealing with a diabatic system and we are dealing, assuming potential energy 0, or negligible, assuming kinetic energy is negligible, then dH is basically minus dW. And it's that expression which we're using to compute work in terms of enthalpies. Now, when we condense the mercury vapor, heat will be released. Heat will be released. Remember, this is operating at a higher temperature. The mercury system is at a higher temperature than the water Rankine system. Now, when heat is discarded, the vapor loses heat, there is condensation. That heat will be released, and that heat which is released from the condensation process of the mercury vapor, as being cooled, can be used to heat this steam at this high pressure here. So we have the coupling. So we have a coupling between those two reactions. Let's just call that coupling. Just like your mercury, let's say that's our coupling. Indicate the coupling. That heat which is extracted from the cooling of the mercury vapor can be used to heat our steam, which is relatively also at high pressure. Now, how do you compute? How do you compute this, the efficiency for this dual system or binary system, where we have the mercury system and the water Rankine system? Now, the efficiency of a process in general, we said, was 1 minus Tc over Th. This we derived from our previous discussions on Carnot cycle and the Rankine cycle, the interface Carnot Rankine cycle, and so forth and so forth. So they're in the earlier lectures, they're available. And this, of course, this corresponds to Qc over Qh. And remember, the Qc and Qh refer to the heat from the hot body and the cold body. And we had the heat engine, then work was being done. Now, if we call for our first system, let us say for the first system, the efficiency is 1 minus Q2 over, let's say that's, we have our 1, that's Q3, let's say Q2 over Q1. And then for the second one, efficiency 1 minus Q3 over Q2. Remember, very important for you to remember, the interface between those two cycles is captured in the fact that when you're extracting heat from the mercury vapor, that heat is added. That heat is added to your boiler system, so that as this steam is being heated in the Rankine cycle, it receives that additional donation of heat from the condenser of the mercury cycle, which operates at a much higher temperature. Now, when you are talking about the efficiency of these two systems, when you're talking about the efficiency of these two systems, you don't add them. You don't add them. You don't say, let me take the mean value. No. They are interfaced. So they are interfaced. Remember that we have the high temperature in the mercury system, we have the low temperature in the mercury system, and that low temperature corresponds almost to the high temperature of the water Rankine system. So they are interposed. They're interposed. So it's not a simple question of taking the means. So let us work with our systems here, so that you see how we will obtain our expression, which will enable us to calculate the efficiency of this dual system. So Q3 can be expressed, if you express Q3, we can express Q3 as E2 minus 1, E2 minus 1 plus minus Q3 over Q2 is E2 minus 1, or Q3 is equals to 1 minus E2, 1 Q3 is equals to 1 minus E2 Q2. And so, if we substitute that, the expression, the first expression there, we'll have 1 minus 1 minus E2 Q2 over Q1. And this Q2 from the first expression for the efficiency there, Q2 is equals to E1 minus 1 over Q1 minus, so Q2 here is simply 1 minus E1, 1 minus E1 Q1. So if you substitute that in that expression so that to get the combined efficiency, we are going to have 1 minus E2 to Q2, which is 1 minus E1 Q1 over Q1. Of course, the two quantities will cancel themselves out. And this expression here will be reduced to the form where we have E combined, the combined efficiency. Combined efficiency will be 1 minus, we open up this bracket, we multiply this bracket, this quantity, and that quantity. So 1 by 1 will be 1. 1 by 1, 1 by E minus 1 will be E minus 1. And then we have minus E2, E1, so we have minus E2. And we have minus E2 times minus E1, that will be plus E1, E2. And of course, if you open those brackets, you'll have 1 minus 1 plus E1 plus E2 minus E1, E2. And that will cancel so that the combined efficiency will be, for our system here, E combined will be E1 plus E2 minus E1, E2. Now, if you look at that, it's far from the average. Average would have been efficiency of E1, system 1, that is the mercury, system 2, that is the Rankine cycle. So it will be, if it will be E1 plus E2, you can see how simplistic it is and how inaccurate it would be. Let us just say, for example, now that in that particular system, let us say that we have this hypothetical problem. Let us say that the mercury system, that's just a hypothetical problem. Where we have just picked some efficiencies. Let's say that the efficiency of the mercury cycle was, for the mercury cycle, was, let's say, 20%. And for the water Rankine cycle, let's say is 10%. This is just hypothetical. And of course, you know, when you're talking of efficiency is output over input, whatever quantity, work output over input. So we talk of percentage, but we normally give them, we divide by 100 so that we get the actual value. So this would be 0.2, which is basically 0.2, and that would be 0.1. So let us look at the combined efficiency of that system, of that particular system. Let's look at the combined efficiency. Let us see. The combined efficiency, E combined, will be 0.2 plus 0.1 minus 0.2 multiplied by 0.1. And so this gives us 0.3 minus, that is 2 to the power 10 minus 1, and that's 1 times 10 to the power minus 1. So that gives us 2 times 10 to the power minus 2, which will be 0.3 minus 0.02. And if we look at that value, so we have 0.30, 0.02, 02. So that gives us 0.28. So this gives us 28% efficiency. Now, what is the significance of this result? The mercury cycle had 20% efficiency. The water Rankine cycle had 10% efficiency. We notice that the efficiency, the combined efficiency of the binary vapor cycle is greater than either of the individual efficiencies. Very important. The efficiency, the combined efficiency of the binary system is greater than that of the individual systems. In this case, we are talking of water, mercury systems. Very important. Is greater than that of the individual systems. So it's significantly different. Suppose you had decided that I'll just take the mean. You can see what would have happened. The mean value would have been 0.2 plus 0.1 divided by 2. That gives you 0.15, which will be 15%. Totally inaccurate. Totally inaccurate. Totally inaccurate. Very important. So even if we have a network of systems, the pattern will basically be the same. Yeah, we have added the efficiency, the first one, subtracted from the product. So if you do for multiple systems, the pattern will still be the same. And so you can try to exercise with that. But very important for us to note that this binary system, mercury, plays a very, very important role as compared to water. While it has very low specific heat, mercury has very low specific heat compared to water. I think mercury specific heat is about 0.13 kilojoules per kilogram per Kelvin, and for water is about 4.18. But the density, what is the significance of that? Because of the density, you can recycle back mercury into the turbine. You can recycle back the mercury into the turbine. Let's just mention those few advantages. Very important for you to know that you can recycle the mercury. Back. And that's as a result of its density. You can recycle it. That's a very important thing. And in the temperature entropy diagram, remember when we interfaced the Carnot cycle into the temperature entropy diagram, we had that system S. Remember that? It's in the earlier lectures. 4, 2, 3, 4, 5. That's isothermal. That is isentropic. Isothermal, isentropic corresponds to adiabatic. They are in the earlier lectures which we have discussed. Now, with the mercury, because of these qualities of mercury, the specific heats and so forth, it approaches this circle. It approaches this circle very, very closely. It approaches this Carnot circle in the temperature entropy matrix. So you'd prefer it. And of course, remember, because of its high density of mercury, by the way, is very poisonous. It's very, very poisonous. And if you see it has very strong cohesive forces. Mercury has very strong cohesive forces, so it's normally globular. The cohesive forces are very, very strong. It's very poisonous, so as we handle it, we have to handle it with a lot of care. But remember, because of its properties, it closely resembles the Carnot cycle in the temperature entropy matrix. And the other thing, because of its density, it has low jet velocity. So remember, if you look at the Pelton turbine, we discussed that in earlier lectures there, and we talked of the nozzle and we spring the steam on those blades or those vanes or blades. So it will have low jet velocity, that is true, but it has high density. It compensates for that. That will be compensated for by the high density. And so mercury has all the advantages. Yes, has low latent heat, fine, but has a high boiling point, as a high boiling point. And like we have said, because of those density elements, we are able to do a few things with the mercury. So we'll stop at that point in terms of the efficiency, combined efficiency of binary cycles.